guys hear me? We're, okay, thanks, Vincent.
Let's go ahead and try and get these guys started. We'll keep the show rolling. If you wouldn't mind, grab your seats. It's my pleasure to introduce Aaron Calvert, Dylan Berzina, and Vincent Brooks to talk about their Baja SAE frame design for the 2016 competition. For those of you who don't know, they competed this past semester, so just a few weeks ago, and they did a great job. Pulled a 42-hour night that I'm sure they're still recovering from. So with that, go ahead.
Good morning. Like we said, I'm Aaron Calvert. This is Dylan Berzina and Vincent Brooks, our advisor. He didn't introduce himself, but his name is Dr. Julian Davis. We're the 2016 Baja SAE frame design team. A brief overview. We'll go over our team's objective. We'll also be going through some Baja SAE background of the competition, some subsystem breakdown for our vehicle, the frame design and the whole vehicle itself. We'll go through some goals that our team set up early into the project for the whole frame as a whole, and then some SAE specifications that restricted our designs and material usage. We also will go into depth of our design phase and the stress analysis of the frame. Then we'll go into the frame construction, and then finally our project budget. Our objective was to conceive, design, and build the frame for the 2016 USI Baja team and competition.
Now you may be asking yourself, what is Baja SAE? Well, it's an intercollegiate design competition run by the Society of Automotive Engineers. Established in 1976, the first competition was limited to 17 members, 17 schools. The previous competition that we were in hosted 120 of them. It is an off-road vehicle design which focuses heavily on the machine design element of mechanical engineering. And in this competition, students compete against each other, against other universities after building a vehicle which must first pass a rigorous technical inspection, and then it must be able to withstand the event conditions of all of the dynamic events. Speaking of which, there are 4 dynamic events. The first one is the acceleration run. The acceleration run is essentially a drag race in which 2 cars are pitted against each other and then tested for their velocity, how fast they can reach a certain velocity. The maneuverability event is next, and this is a test of the car's agility and steering. This is then followed by the hill climb, which tests how much power the vehicle has and how fast it can come up a hill, or if it can go up a hill at all. This is then followed by the suspension and traction event, which tests how much the vehicle can handle rough terrain. All of these aspects are then combined into a 4-hour endurance race in which success is measured by how many laps the vehicle can complete within 4 hours.
For the system breakdown of a Baja vehicle, you have the frame, the suspension and steering, drivetrain, and brakes and safety. For our design, our focus was on the frame, which includes the front, the cockpit, and the rear. We also had another senior design team that worked on suspension and steering, so we had to communicate with them frequently. We also had to design the frame around the drivetrain, which is the engine, the gearbox, and the differential. We also had to keep in mind the brakes and safety. We wanted adequate safety for the driver at all times throughout the event. So we had 3 main goals for our design. We had dimensional goals, system integration goals, and structural integrity goals. For dimensional goals, we wanted to shorten the overall length. This will improve the turning radius. We wanted to reduce the overall weight, which ultimately will increase the speed. We wanted to minimize the volume of the rear space. This will have more potential for agility. We also wanted to lower the front height. This will improve visibility for the driver. For system integration goals, we wanted to improve the integration between the Baja vehicle systems, such as suspension, drivetrain, and the driver. This will improve the ergonomics and handling of the vehicle. And for structural integrity, we wanted to have a minimum factor of safety that's greater than 1. And we'll talk about factor of safety later on in the presentation. But with factor of safety greater than 1, we believe that the vehicle will be safe for the driver during any impact collision.
SAE specifications, the frame design and build is required to follow some rules that are laid out. The Baja vehicle itself cannot exceed a width of greater than 64 inches. The vehicle cannot be longer than 108 inches. The drivers themselves cannot be taller than 6 foot 3 inches or weigh more than 250 pounds. The frame is restricted in what it can be made of. It can be made 4130 chromoly steel. The primary members are 1 inch outer diameter by 0.12 inch wall thickness, and then the secondary members are 1 inch outer diameter by 0.035 inch wall thickness. This figure here shows all the members that Baja SAE restricts us and enforces that they must be made out of primary members. All the other members of the frame can be substituted for using secondary members. A complete rules listing can be seen on the SAE website.
From the previously used frame shown to the left, 3 other designs were inspired for this 2016 design. Each design had their own primary motive, and our first design's primary motive was weight. The second and third designs emphasized reduction of rear volume and length, respectively. So in our first design, not only did we achieve a new weight of 56.3 pounds, we also achieved a new length of 78.49 inches, a new rear volume of 9.5 cubic feet, and a new front height, or nose height, of 16.36 inches, all with a factor of safety greater than 1. However, we failed in the aspects of suspension integration, drivetrain integration, and driver integration. For suspension, the suspension has these components called A-arms, which are used to attach the wheels to the car, and they did not have the right dimensions to fit with the front of our frame. The drivetrain and the driver had insufficient spacing for the driver's feet, and this other component to the drivetrain called a differential, which did not have enough space to be mounted properly.
Design 2, our goals was primary motive was rear volume reduction. We also improved the new length of reducing it to 74.25 inches. Also a new weight of 67.9 pounds. The rear volume for this design was 10.17 cubic feet, and then a new height at the front of the vehicle was 18.95 pounds. In this design, it failed again with suspension integration. The A-arms did not comply, were incompatible with the front of our vehicle. The drivetrain did not fit within the confines of the rear of the vehicle. And then our driver also again had insufficient spacing for the feet. But the primary cause for this fail was in the rear during a crash we simulated, it was found to have less than 1 factor of safety, which we felt was insufficient for this design.
So for design 3, our primary goal was to reduce the overall length. This new length was achieved at 75.5 inches. We also achieved a new weight of 81.95 pounds, a new rear volume of 11.26 cubic feet, a new front height of 20.66 inches. And this design actually integrates well with the drivetrain in the rear, and also the driver's seat in the front. He had enough room for his feet. This design also failed once again in suspension. The A-arms in the front were not compatible, and the factor of safety in the rear was once again less than 1.
However, we did end up choosing design 3 as the most well-rounded of these 3 designs. So the 2 adjustments we made were to straighten out the front end to better comply with the suspension design, and add 5 secondary rear members, supporting members, to the rear end to increase the factor of safety to that greater than 1 mark that we wanted. And here is the final design with all of the enhancements that we made, including the mounts for the drivetrain and suspension. You can see the rear members in the back and the straightened out front end for the suspension in the front. Notice the color differentiation. The black represents primary members and the blue represents secondary members.
So once again, here's our final design. On the left, you can see the suspension and the steering are integrating with our frame. And on the right, we have the drivetrain, which is integrating with our frame as well. You can see the engine and the gas tank, transmission, and the differential all are fitting within the limits of our frame. So our accomplished goals compared to the previous red frame, we had an overall length reduction of 11.33 inches. The frame weight was reduced by 9.62%. The rear volume was minimized by 9.29 cubic feet, and the front was lowered by a total of 6 inches. So next we'll move into how we determine our factor of safety. This was done through a process called finite element analysis. And for this, we tested 4 worst-case scenario impact collisions. We had a forward impact, an aft impact, a lateral impact, and a rolling impact. And next, Aaron will go into the calculations on how we figured this force.
For our impact calculations, we had a total mass of 20.96 slugs. This is including of driver and vehicle. In layman's terms, it's about 510 pounds. We also had, we tested with a velocity of 40 miles per hour. This is considered a worst case scenario. The average velocities during this competition are between 25 and 30 miles per hour. And then travel after impact was calculated at 5 feet. Our final force was calculated at 1,558.7 pounds. This force will be applied as a worst case scenario to all of the impacts that we'll go through now.
Now to explain factor of safety, there's a scale to the right, which represents the maximum stress our vehicle can withstand before it begins to bend or yield. This is called the yield strength, and in our case, it is 66,717.36 psi. Now, if that yield strength is met, the factor of safety is equal to 1. If it is exceeded, the factor of safety is less than 1, and if it is less than the 66,000, the factor of safety is greater than 1. So in our front impact scenario, we applied a force to the bottom front end of our vehicle, and we applied fixtures to the firewall. And this force represents what would happen after a suspension event or endurance race where the car lands off of a cliff, not cliff, but lands off of a hill, and it makes a dip into the ground and has to come back up. So using that applied force of 1,558.7 pounds, we ended up with a maximum stress of 29,851 psi with a minimum factor of safety of 2.23. This is adequate. The rear impact represents what would happen if another car were to collide with the rear of our vehicle. And so we applied the forces at the rear, applied fixtures to the front, and our maximum stress here was 44,034 psi with a minimum factor of safety of 1.5.
Next, we have our lateral impact and rolling impact. For the lateral impact, this simulates the vehicle has crashed into the side of our vehicle. So here, the force of 15,058.7 pounds was applied to the left of the vehicle and was fixed at the firewall. This provided a maximum stress of 60,937 psi with a factor of safety of 1.1. For the rolling impact, this simulates the vehicle has flipped over on its top. So a force was applied at the top of the vehicle, and the fixtures were applied at the bottom. This gave a max stress of 46,836 psi and a factor of safety of 1.4. So keeping in mind, these are worst case scenario collisions. So with a factor of safety that's greater than 1, the frame will not deform if it's under a collision and will provide adequate safety for the driver throughout all the events.
After we were done with our design phase, we began construction. Our materials arrived after being purchased on December 16th, 2014, and our final design was finalized on the 18th. We began construction on that day. The materials we used, again, was the 4130 chromoly steel. For the primary, we used the 1-inch outer diameter by 0.12 inch wall thickness. And then for the secondary members, we used the 1-inch outer diameter by 0.035 inch wall thickness. The 1018 steel we used for making mounts for our systems to our frame. We will be making mounts for the engine, the suspension, and the drivetrain.
We used a Lincoln Electric PowerMig 255 for all weldments to the frame. We used a Bailey Industrial tube bender to bend the frame members into shape, and a DeWalt circular saw to cut the frame members. It's shown to the top right. And you can see to the bottom right a Craftsman 15.5 drill press with a Milwaukee notcher, which was used to fish mount the frame members, and this was to facilitate welding.
Some problems arose during the construction of our frame. We found that the secondary tubing was too thin to be bent without kinking. We attempted a solution by filling up the members with sand and then capping both ends before bending. Fortunately, this also resulted in the members kinking, which would be unusable for our frame. This required a substitution for all of our secondary members that we designed to be bent. We substituted them with primary members for the construction. This final weight addition to the addition of primary members was added to the weight, and it is part of the FEA analysis that you saw earlier. We also had some bending errors at the very beginning with misinterpretation of the bending, which direction the benders bend the material, so we had to refabricate the front and rear overarching members. Our build progress, on the left here we see the jig laid out. This facilitates the shape and structure of the bottom of the frame.
And to the right, you can see the addition of the lateral cross members. In this picture, the members still have to be notched and welded to the bottom member.
After we notched those lateral cross members, we welded them together and the bottom of our frame was finished.
And to the right, you can see the cockpit begin to take form with the welding of the overarching top members and the firewall.
The cockpit takes even more shape with the addition of the side impact members to this frame.
And next we have the addition of the nose, and this has enough room for the driver's feet and also complies well with the front suspension.
With the completion of the front of our frame, we added the overarching rear members to the frame. This facilitated the shape of the rear volume, which we minimized from the previous frame design.
And to the right, you can see the current status of our frame as it sits in the Applied Engineering Center. What's missing from this frame are the motor mounts, the drivetrain mounts in general, as well as the suspension mounts. We're also missing those rear supporting members and the front and rear hitch point members, which would be used to tow the car. And these are going to be completed upon completion of the other subsystems, such as the drivetrain and the suspension.
So the cost analysis for our materials, primary and secondary 4130 steel. We approximated 37 feet of both. We ordered 100 feet of both. This was due to the lack of experience welding and fabricating this type of material. So the primary cost $530, the secondary cost $233, and then our mounts, the 1018 steel, cost $17.26 for a total material cost of $780.26. Our labor cost, we had our advisor, Dr. Davis, as well as Aaron, Vince, and myself. We had a total of 248 labor hours for a total of $9,612.
Lessons learned, if we were to start again, we would design for multiple secondary member usage. For all of our bent members, we would use the 1-inch outer diameter by 0.065-inch wall thickness. And we would continue to use, for all the strength secondary members, the 1-inch outer diameter by 0.035-inch wall thickness. We'd also have preferred, at the beginning, to communicate more frequently with the suspension team design.
In conclusion, our objective was to conceive, design, and build a frame for the 2016 USI Baja team. And we completed all of our design goals in that we have a reduced final weight, reduced rear volume, reduced length, reduced front height or reduced nose height, and we also improved system integration and raised our minimum factor of safety in any scenario to 1.1. The only things left are the mounts and the rear supporting members, as well as those front and rear hitch point members. We would like to thank our advisor, Dr. Julian Davis, for overseeing this entire project and keeping us on schedule, as well as Drs. Glenn Kissel, Natasha Smith, and Paul Cuban for overseeing our presentation dry runs. We would also like to thank Dr. Zane Mitchell for approving this project, and Mr. Justin Amos for helping us build the frame in the AEC, as well as Mrs. Donna Moore, the engineering administrative assistant, for ordering all of the parts for this project. We'd also like to thank the USI Baja team for their contributions, and the Pott College of Science and Engineering, without all of whom this project would not have been possible.
Questions?
Is there anything from this year's competition that would make you rethink what you've done for next year's, what you are to build here?
One thing specific, can you guys hear me? Dylan's got one. That works too. One thing we specifically changed after this competition was to redo one of the FEAs. We were originally going to have a front impact scenario where our car is just colliding with another vehicle, but we found it was much more catastrophic to the integrity of our frame if the vehicle were to land in a pit or land from suspension. So we wanted to make sure that we had that fixed. That was determined to be the worst case scenario.
So we had it before us here at the bottom, we had that collision during the race. We had that.
I actually have a question about that slide also. Not so much where you applied the forces, but where you applied the red parts, the constraints. Because if you were to fall off of something, wouldn't it be an inertia question?
Yes, it would.
How would you maybe try to simulate that on an element?
Well, we'd have to reapply the fixtures to somewhere other than the firewall, but honestly, we were more concerned with the forces than the inertia.
Yeah, but when you're decelerating, don't the inertia give rise to the forces?
Yes.
Good job, guys. Obviously, a welded construction, is there a particular spec for the weld process? And was it tested?
Yeah, we had to make weld samples. Whoever welded the frame had to take the competition, and they had to break them, or we broke them, and they had to see that we had adequate welding methods.
They had to break, not at the weld, but the bars had to break first.
Any other questions?
Based on some of the issues that we ran into with access to the engine and drivetrain on the current car, I noticed you guys had a secondary member that comes across. It's an angle brace that kind of covers the entire side of the CVT. With that being a secondary member, is it possible to have a removable member of some sort to ease access to the engine?
I don't think we're allowed to have removable members. Did you have that picture?
You know, the reason I have some roll cages for street and strip drag cars, they will have a two-piece mount with just basically a pin or a bolt to put it in place where you can pop that out and then have a hinging bar. I felt like that could be useful if it's legal.
You can do a bolted frame, so maybe for one member we would be able to do that on one side.
Good job, yes.
Any other questions? All right, let's give them a hand.